Okay, one more tool. Right, we've got one more tool that we're going to add to our toolbox for finding the roots of a polynomial, and it's got a name here, right? It's called Descartes' rule of signs, named after Rene Descartes, who I'm sure, hopefully, you've all heard of. The whole Cartesian coordinate system, the whole idea of doing geometry on a grid was Descartes' idea, and his rule of signs, it looks really, really wordy. And it's one of those things, it's easier to show than it is to put in words. But we'll talk this through real quick before we go on and look at some examples. First, it says, let p of x be a polynomial, and this is an important part here, written in the standard form. In other words, with the exponents in decreasing order, just like we always write it, x to the fifth plus x to the fourth plus x to the third, for example, not x to the fourth, x to the fifth, x to the third, right? Everything in the usual order. Then, the number of positive real roots, so that's what we're talking about here, right? This theorem tells us how many positive real roots there are, and it has to be equal to either the number of sign changes, we'll talk about what that is when we look at an example, in the coefficients, or that number minus an even integer. Okay, and then this next part, that's positive roots, right? If we want to find the number of negative roots, all we have to do is calculate p of negative x and then use the exact same counting process on that polynomial, and we'll get the negative ones. Okay, so like I said, easier to look at examples. Right, so look at this thing. Right, I want to discuss the number of real roots. Specifically, I want to talk about how many positive versus negative ones there are. And what Descartes' rule of signs says is we count the number of times the sign of the coefficients change. Right, so I'm looking at this polynomial. The first coefficient is positive. The second coefficient is positive. There was no change in sign. Going from the 2 to negative 7, okay, there was a sign change there, so that's 1. Negative 7 to 2, that's another sign change. Positive 2 to negative 3, that's a third. And finally, we have negative to negative, that's not 1. So this polynomial has 1, 2, 3 sign changes. So what Descartes' rule of signs says is the number of positive roots is either 3 or, and this is the subtract multiples of 2 part. I'm going to keep subtracting 2 from this number until they become negative, because obviously there can't be a negative number of roots. So 3 minus 2 is 1. That's also a possibility. 1 minus 1 is negative 1. Can't have a negative number of roots. That's where I'm going to stop. Right? So these are the possible number of positive roots of this polynomial. Okay, so now how about negative roots? Well, negative roots, remember, we're going to do almost the same thing. First, I'm going to calculate p of negative x. That's negative x to the fifth plus 2 negative x to the fourth minus 7 negative x to the third plus, that was supposed to be an x squared here, plus 2 negative x squared minus 3 times negative x minus 2. Now you see what we've got going on here. All this comes down to is straightening out negative signs. Negative x to the fifth power is negative x to the fifth power plus negative x to the fourth, that's positive x to the fourth. So this stays 2x to the fourth. All right, here I'm going to have, this becomes minus x to the third times minus 7 is plus 7x to the third plus 2x squared plus 3x minus 2. Okay, now I count sign changes again. The sign changed here from negative 1 to 2, and it changed, and it stayed positive, right? From then on, until we get to the very end where it changes from positive 3 to negative 2. So there are two sign changes here. So Descartes' rule tells me that the number of negative roots is 2, and I do the same thing with the minuses. Start subtracting 2's, right? 2 minus 2 is 0, so it's possible there are no negative roots. That's an acceptable answer. And again, now here if we subtract 2, we get to negative 2, and you can't have a negative number of roots. So there are my answers, right? There are either 2 or 0 negative roots, and either 3 or 1 positive roots. Okay, so I got another one here, a little bigger, 7th degree. Why don't you go ahead and pause, right? Take a look at this, see if you can answer the same question about the number of roots with each sign. Right, so let's count sign changes. Right, we're doing the positive ones first. So I've got a sign change here from positive to negative, here from negative to positive, and here from positive to negative. So I've got 3 sign changes, which means there are, it's supposed to be an H there, there are either 3 or 1 positive roots, right? 3 minus 2 is 1. Okay, now for the negative ones, I got to look at P of negative x. That's negative x to the 7th plus 3 negative x to the 6th plus 2 negative x to the 5th. Whoops, got my parentheses out of place there. There we go. Minus 4 negative x to the 4th plus 3 negative, I know these get long, negative x to the 3rd plus 2 negative x squared minus 4 negative x minus 4. Do you see the pattern? I mean, there is a pattern to this. The sign of every term that has an odd exponent is going to change, and the signs of the terms with the even exponents stay the same. So this becomes negative x to the 7th plus 3x to the 6th minus 2x to the 5th minus 4x to the 4th minus 3x cubed plus 2x squared plus 4x minus 4. Now that I know my pattern, I'm going to do a quick check against the original, right? And I'm seeing which ones change. Only the odd exponents are changing sign. Good. Yes, that's what I needed to happen. That's what I expected to happen. So let's see, I got a sign change here from negative 1 to 3, here from 3 to negative 2, here from negative 3 to positive 2, and here from 4 to negative 4. So there are 4 sign changes, which means there are 4, 2, or 0 negative roots. Okay, so that's really all there is, right? That's all there is to Descartes' rule of signs. And it may not seem like the most powerful theorem in the world. I mean, it's kind of a neat trick, but it's not really telling us what the roots are. But I want you to think back to our discussion of the rational root theorem. The rational root theorem gave us a list, and sometimes it was kind of a lengthy list. And what Descartes' rule of signs is going to do is it's going to help us narrow that list down. For example, if Descartes' rule of signs comes back and says there are no negative roots, then you can cross the negative roots off of your list. That literally just cuts your list in half, right? And if Descartes' rule of signs says there's only one positive root, once you find it, cross all the others off, right? You know all the others aren't already. So that's where this theorem is going to come in useful, right? It's going to be a tool for narrowing down what otherwise is maybe a really long list. Okay, so where are we going next? So far, we've really been focused exclusively on real roots, which is fine because graphing has been a big theme for us, and we're always graphing things in 2 dimensions. But sometimes you do want to take that next step and find the complex roots as well, right? So in the next lecture, next couple of lectures, we're going to talk about how to find the complex roots of a polynomial. And then we'll wrap this section up by looking at some examples where we start with just a generic polynomial, and we bring all of these tools together and see how we can use them to come up with a complete factorization.